Good morning, everyone. Please take a seat. It's again my pleasure to welcome you in Paris La Défense and at the Ministry for the second day of our symposium, which will be dedicated. So yesterday we had general presentation of products, etc. And today it's really dedicated on applications. So we have a first session with 6 talks, and then a panel discussion on the presentation. So it's a mixture of presentation of case studies and also of other types of application from the projects. And we will have a second session which will be chaired by Alberto in the end of the morning with more energy industry perspective and business. So I would like to first welcome and ask Laurent Dubus from EDF to present the demand modeling for pan-European continent.
Thank you, Robert. Good morning, everyone. So this would be a quite quick overview of what we developed in ISEM for the demand modeling over Europe, so the pan-European level. You know that with the program we will have time for exchange and asking questions and so on at the end of this session, but also during the meet the expert session this afternoon. So in case there are questions, we can answer them then. So the outline of the talk is that one. I will remind you what our targets were within the contract, and then I will spend a little time describing the modeling approach, both from the data point of view and the models point of view, and then I will show how we did that on the historical period, so the last 40 years or so, and then for the projections, and give some conclusions. So you have already seen this project structure for ISEM, and so we are talking here about the War Package 3 mainly, in which we try to build those time series for demand and for generation from different sources. The targets for that, and for demand specifically, was really to work at the European level, including all the countries, or most of them. The time resolution we aimed at working at was daily. We could have done 6 hourly based on interim data, but we chose to work at daily time resolution because first it's a proof of concept, so we didn't go into too much details, and it was easier to handle inside the demonstrator because the files are lighter and so on. But in principle, we made tests at 6 hourly resolution, and the results are very similar. And so we worked on 2 different time scales mainly. The first one is the past 38 years, let's say 40 years, so from 1979, that's to say the start of era interim, and then with the projections from 1979 to 2050 or even 2065, because we wanted to have also 30 years averages centered on 2050, so that's 2035 to 2065. The modeling approach is very standard, and then there's nothing really original in that. So we use climate data, which have been bias adjusted by Work Package 2 in SM. I will come back to the data themselves later. And we also need energy data to set up the models. So in this case, as already mentioned yesterday, we choose to use the ENSOI database. So ENSOI, for those of you who are not familiar with that, is the European Network of Transmission System Operators. So that's the association of TSOs in Europe. So involving all the national TSOs, for instance, RTE in France, National Grid in the UK, and so on, which is in charge of many things, and among those things, there is, since regulation number, I don't know what, a few years ago, one of their rules is to provide data sets in what they call the transparency platform, which has been released in early 2015. And at the end, what we want to get with our models, and I will detail a little bit more just after, is to simulate energy variables on long periods, so on the run analysis timescale, climate projections, and also seasonal forecast, but we worked less on that for demand because it was more complex. And one important thing in that is that we are working for Copernicus, and Copernicus is open access and so on, and so we needed to rely on public data sets so that it can be made available to anyone at no cost. And the other constraint, of course, is that we wanted to have an homogeneous and coherent approach at the European scale, and so ENSOE is obviously the main source of information that we can use, and to be honest, I think it's the only one that is available. So about the data from ENSOE, so the reason I already explained is that ENSOE has set up its transparency portal. So data is available for most countries in Europe with different lengths of the time records depending on the countries. For demand, for instance, most countries have daily data back to 2004. Some of them have started delivering data later. Some of them, for instance, for Albania, at the start of the project, we didn't have any data, so Albania is not treated in the contract. And the advantage of that portal is that in a single place you find all the data for all the countries. It's a very good step forward, but however there are still some problems in this database because there are some posteriori checks which are made and some updates which are made and so on, and the metadata are not fully satisfying, so there are still problems in the database, but it's a very good start and it's improving over time. So for future activities, I think it would be really the basis on which to rely, and everyone in this room, I guess, who is interested in developing climate services for energy sector should increase their interaction with ENSOE. ENSOE also publishes annual statistics, which are official and validated data, so it's delayed in general. For instance, for the installed capacities of wind or whatever you want, you have probably more than 6 months delay between the publication of the data and their date of validity and so on. But yeah, once again, it's a very good database to work with. We also used other data sources, for instance, from the World Bank, for some countries where we didn't have data from ENSOE, and we had longer time series from the World Bank, but it's only at annual resolution. And we also used national TSOs and other databases. So the demand modeling, I tried to be brief on that because yeah, you've probably seen there's a poster outside, and we can discuss the details later. But basically, you have a trend in demand that you can see on for example, on this plot for France. This long-term trend is due to economic activity, population changes, and so on. And so when you want to model the climate part of the demand, you need first to remove this trend. So that's why we did this modeling in 2 steps. So the first one consisted in using the monthly data back to 1991 for most countries, set up a GAM model, so it's a generalized additive model, to remove this long-term trend. And once you have done that, you can interpolate this trend at daily time step, remove it from the full signal, and so you get a detrended daily time series of demand without the effect of economic activity and so on. And then these residuals can be modeled taking into account climate variables. So in this case, we used, depending on the countries, but for most of them, we used temperature, solar radiation, wind speed at 10 meters, and relative humidity. Not all the 4 parameters for all the countries, but temperature was for sure there for all the countries. And you also need to add other predictors, which are calendar data. So is the current day a weekday, a weekend day, a holiday, and so on. And you can set up GAM models as well for that, and then you get a model which predicts the trended demand. And from this, of course, you can compute relative anomalies and so on. So at the end, you have different models. So one of them, here it's all with the trends. But if we just look at this one, so this is the full signal reconstructed. So you have your detrended model to which you can re-add the trend that you initially removed, and you finally get this signal. So for instance, this is for France. So this is the data from NSOE in blue we had at the beginning. And once we have set up the model on this period, we can recompute the full time series back to 1979 using the full error interim dataset. And you can see that the fit is very good between what is modeled and what is measured. Of course, there was a cross-validation over the period, so maybe 2/3 of the years were used to set up the model, to calibrate it, and then the rest of the time series was used for verification. Here you have some validation for France, and you can see that on overall, the mean absolute percentage error is around 2% in that case, which is very good. It's not as good as operational models, which are closer to 1%. But anyway, it's very good for the purpose of the service. For the projections, we use the same models. So we set up the models over the historical period. And then we use those models with the time series of climate variables from the climate projections. So both for RCP 8.5 and RCP 4.5. So we got the detrended projections at a mean level which is similar to the current level. And then in addition to that, we used also the 5 EIOA scenarios that Alberto introduced yesterday, which were proposed by the EIOA project, and which provide some mean levels of consumption over the next 50 years or so. Just to show you what those scenarios give for 3 different countries, you have the 5 scenarios, and you can see what is the mean level of demand that those scenarios provide. And in fact, what we do with ESEM by adding the RCP scenarios and the variability which is inside is to add noise or variability around those mean scenarios and to provide the full picture for the future. So a few plots now. So this is just the time series over the historical periods, over the error interim period. So you can see in, the colors are really different, but the reddish color there, you can see the signal including the trend, and the other one, which should be blue, is the detrended signal. So you can see that we more or less remove the trend due to economic activity. You can, so this is again about the historical period. You can, of course, with the demonstrator, plot many things. Here you have 3 different countries with annual values. Yeah, because I forgot to mention that the data is provided at daily resolution, but you have also the monthly, seasonal, and annual values. So here we can see the different trends for different countries, so France, Germany, and UK. If you here you have an example of seasonal values, so you can see the annual cycle in the demand. And here you have the same signal expressed in terms of relative anomalies. So we just add the detrended signal, remove the mean and divide by the mean. And you can see here for 2 different countries. So France is in red, something which looks like red. And what you can see on this plot is that we perfectly find again the main demand anomalies over France in the last 4 decades. So for example, the January 85 cold event, which means an anomalously positive demand. We also find a cold spell from January 2010, December 2010, and February 2012. And in April 2011, it was very warm in France, and so the demand was much lower than normal. So we can find those events again. I won't go into the verification statistics, but this is explained on the poster outside. But as I mentioned, this is a MAPE value for all the countries, and except for a few ones, especially Luxembourg and Switzerland, for which we had problems with the NSOE data, all the models give quite good results with about 2.2 to 2.5% of MAPE, which is very good, according to our experts. For projections, a few example plots as well. So here you have, for France, you have different curves. The blue one is the historical period, including the trend. The reddish one is the same, but with the trend removed. And then on top of that, we have two different projections. So the green line here is the detrended projection. Okay, is the detrended projection for France, and in yellow here we have added the mean level of one of the scenarios from Highway 2050, and we can see what it gives. And the good thing is that we can see that the climate scenarios are in the same range as the analysis over the past. I will not go into much details, but with the demonstrator you can, and you will be able to explore it this afternoon. You can plot different countries on the same plot. You can plot different RCP scenarios. You can plot different EIW scenarios and so on. I will just show two results now. This one is, in fact, it's one of the most important results with the demand projections, is that here we have the summer, so June, July, August, and winter, so December, January, February, evolution of demand from the 1980s to 2060 for Spain. And we can see that there is a reverse trend for both, so a decrease in winter consumption and an increase in summer consumption. And Robert is making big signs in front of me, so I won't explain the other figures, but you will have them and you can play with the demonstrator. I just want to summarize by saying that the models we have built, so there is one model for each country. They have been validated for the historical period and used for the projections. And I want to insist on the limitations, which are that our projections for the future do not take into account any change in the technology. That's to say, for instance, energy efficiency measures and so on by construction. What we wanted to see was the impact of climate variability and climate change on the demand, considering the shape of the demand is equivalent to what we have today. But so we managed to show that. And the main signals are the one I just mentioned. So more or less a decrease in winter energy consumption in most countries due to increase in temperature, and an increase in summer energy consumption, in particular in countries where there is already some significant air conditioning installed currently in Europe. That's to say mainly in southern countries. Thank you.
Thank you, Laurent.